by Aronson here.
Yeah. All right. So I'm Daniel. I'm going to be talking about the classification of reversible bit operations. This is joint work with Scott Aronson, who's now at UT Austin, and Luke, who I'm supposed to remind you all is awesome. So the motivation for this whole work, you kind of like the holy grail of classification is, I hand you a set of quantum gates, and you should tell me which unitaries they generate. And I'll get into exactly, what notions of generate I mean in a second. But for example, some gates that are obviously not universal. The 1 qubit gates. These are just can't create any entanglement between 2 different qubits. So sometimes pretty useless. Slightly more interesting, classical reversible gates. So this is actually going to be the focus of this talk. But in the realm of the whole classification. They only map classical basis states to classical basis states, so they're not going to be universal for the unitaries. Even more interesting, the Clifford gates. If you're not familiar, this is the set of gates generated by C0, the Hadamard gate, and the pi/4 phase gate. And if you look at the state representation for the sets of states that these gates can generate, they look pretty complex and they have lots of entanglement. But nevertheless, Gausman and Canelo show that in reality, this is just a discrete set of gates that can be simulated by efficiently by polynomial computers. So, classical computers. So, those aren't those still aren't getting you universality. And this is sort of an interesting example. So Toffoli plus Hadamard. You might say, wait a minute. You're like, I know Toffoli and Hadamard are universal for quantum computation, but if you look at their matrix representations. They're both real matrices. So when I compose the gates together, Toffoli and Hadamard, I still get a real matrix, and so I'm never going to generate a unitary, in complex Hilbert space that has complex entries. But so so these are some non-examples, maybe some examples that are universal. Just take a random 2 qubit gate. This is probably going to be universal. It's going to densely generate. The unitaries, or maybe you really like C0, so you take the C0 and you have all single qubit gates. So what I've done here is I've taken all the examples where I know the answer, right? So in general, if you hand me some gates, it's pretty hard to say exactly what they do. This is a pretty hard problem. To give you some sort of idea, like if I just have a 3 qubit system, this is kind of tantamount to classifying SU8, and not even all the subgroups of SU8 are known. So this is hard. So let's move on. Classical gates. So now that you understand the quantum part, let's just focus on classical reversible gates. So the question is now, I give you a classical reversible gate or a set of classical reversible gates, and now I ask you what transformations do those gates generate? They could be universal for classical reversible computation, or they could not be. And if they aren't, then what transformations exactly do they generate? And by reversible gate here, I just mean some bijective function from bits to bits. But you might say, wait a minute, this seems like this problem has been solved before, and you could be thinking about a couple of things. So, you could be thinking about Boolean logic gates. So these are many-to-one functions. And indeed, these were completely classified by Post in the 40s, and in even a very stronger model that we're going to consider in this paper. But this is the regime in which and or not are universal. Another example is the XOR gate generates all linear functions, so it doesn't generate all Boolean logic gates, but it generates some interesting subset of them. So we're sort of looking for the reversible analog to Post lattice, if you will. But you might say, still hold the phone. There's a bunch of research in the 1980s by Bennett, Toffoli, Fredkin, Landauer, all interested in reversible computation. Didn't they solve this problem? And particularly, you have 2 really important, gates. The Toffoli gate, which is a controlled not gate, which is universal in the strong sense, in which in the sense that it can generate any reversible transformation. And then you have the Fredkin gate, which is a controlled swap gate. So you might notice that controlled swap, the Hamming weight of the input has to be equal to the Hamming weight of the output, because it's only swapping things around. So it conserves the Hamming weight. So clearly it can't generate every transformation. But it turns out if you work in an appropriately encoded subspace, the dual rail encoding, then you can do universal reversible computation. And indeed, work by Lloyd, DeVos, and Storm basically classifies all reversible gate sets whenever leftover garbage bits are allowed. So what do I mean by leftover garbage bits, and why is this bad for us? So suppose we're trying to construct some reversible function f. And we have some gate set G, and we build this circuit which takes in our input X, and also it takes in some ancillary bits, and it produces our desired function f on the input, but it also produces some kind of garbage bits on our ancillary register. And so if we think about applying this to a quantum superposition, so now we're in the quantum case again. We apply the same transformation. Well, then you see now we have all these, input-dependent garbage bits lying around in our ancillary register. So if we forget about our ancillary register, then this is going to, destroy our quantum superposition. And if you know like one thing about quantum mechanics and quantum computation, this is bad. So we want to avoid this scenario. So what we're going to insist is that whenever you have this ancillary information here, this 0, you must return it back to 0 at the end of the computation. And so this is going to remove the subtlety when we apply the transformation in quantum superposition. And even more generally, if we have some ancilla A, then it just must be mapped to the same thing. So, okay, with that in mind, we're basically ready to state the entire model in which the classification will be. So suppose you have some set of gates, G1, G2, and a priori we're not even going to assume that this is a finite list. This could be an infinite list. And we're going to say that the class generated by those gates is just the set of gates under the closure of some really natural circuit building operations. For instance, the composition rule. So if we have two gates, then you can compose them together, and that gate is also in our set. The extension rule, if you have some gate, then you also have the gate where you just add the identity, so you can apply it to more and more bits. And then something for our convenience, we're always going to assume that the swap gate is in our set, and this allows us to basically not worry about the orientation in which we're applying our gates. Basically anything we want to do with our gates we can do, and this is just a nice, concise way of writing that. And then finally, as I referred to before, this ancilla rule. So if I have some gate G and it fixes a particular ancilla, then whatever, for all inputs X, then whatever function is left over on the remaining part of the input, we say that that's also in our gate set. And so we'll see an example of some of this in a second. A quick aside here, a corollary of these rules, since we're dealing with reversible gates, a lot of times in gate classification results, you have to worry about whether or not your inverse is also in your gate set. But in this case, we don't, because if we have a gate G that's in our set, we can just apply G to itself multiple times until we get back to the identity. And then obviously some power of G will end up being the inverse, and that inverse will be in our set. So we'll use that later. Okay, so why might we need this ancilla rule? So for one reason is, suppose you hand me the Toffoli gate, and you say, what can you generate with the Toffoli gate? Well, the Toffoli gate is a 3-bit gate rather, and there's no sane universe in which Toffoli doesn't generate a C0 transformation, but the C0 transformation is on 2 bits. So we can just, with the ancilla rule, we can just set one of these bits to 1, apply the rule, and now we have a C0 gate. So in some sense, it eliminates this kind of small n effects, and we can generate small gates from big gates. But also, allows us to do some slightly more powerful things as well. I'm not going to get into totally the details of how this works, but basically, if we have a Fredkin gate and we have the 0 ancilla here, then we can apply the ancilla rule, and get a controlled swap gate. So we can build more powerful gates using this ancilla rule as well. Basically you just need some areas to work to do some side computation. Okay, so what's the theorem? The theorem is basically that we did it. You hand me a set of reversible gates, and I'll tell you it falls in one of the following classes in this lattice. And I'm going to blew it up as big as I possibly could. So what is okay, cool, this works. What are we looking at here? So this is each node is a class as described before, and it's labeled by a generator. So by a generator, I mean some gate that generates every gate in the class. And you'll notice right from the bat that I've only written one or two things in each one of these little circles. And indeed, that's the case. Every class is finitely generated. So a priori, we assume that some things could have infinitely many generators, but it turns out that's not the case. These arrows are indicating containment. So you see the Toffoli gate is up here at the top that generates all reversible transformations. And it contains the class where you just have the C0 gate. So that's a strictly smaller class. Something else to notice is that the lattice is actually infinite. So over here on the right, we have infinitely descending chain of classes that get smaller and smaller, less and less powerful. And we'll get into the reason for that in a second. So what, how does one go about showing that this is the answer? One of the key tools is realizing that every class is not characterized only by its generator, but also by a set of invariants which hold for that. So much like we talked about in the first part of this talk about how single qubit gates can't generate any entanglement, we also have, in the same sense, in the reversible case, these degenerate gates, where basically you have some linear or affine function here, but basically this A is just a permutation. So you're basically just swapping the bits around. You're not doing anything interesting. You could expand the power a little bit and think about just orthogonal gates, where you still have this affine transformation, but the linear part of your affine transformation has to be orthogonal. And this is actually sort of unique to our classification that with our ancilla rule that you get these very interesting interactions between this linear part being orthogonal or not. And then finally, most generally, you have the affine. Well, most generally for the affine case, at least, all you require is that A is invertible. So I could sort of do this for all these boxes in here, but that would probably be a pretty boring talk. So I'm just going to pick one more random one. So mod 4. So these are the classes for which all the functions preserve the Hamming weight of the input mod 4. So you have some x and you apply f to it, and then the Hamming weight of the output is equal to the Hamming weight of the input mod 4. And mod 4 is totally generic here. So I could have picked k for any k, and I would have a class corresponding to that. So that's why we have this infinitely descending chain here, because I could have picked a million, but that would be quite a big lattice. So thinking about the lattice again, so how you hand me a gate, and I want to know which class it falls into. And so you basically just iteratively ask a bunch of these questions about the invariants which it preserves. So for instance, you could ask, does it preserve Hamming weight mod 4? And you say, yes, OK. So it must lie in one of these classes. And you say, is it affine? And I say, no, it's not affine. So it must sort of lie here then. It must be in one of these classes, And then you can ask, does it preserve Hamming weight mod 8 or mod 12 or mod 16? I say, no, it doesn't preserve any of those. So then we know, OK, it must therefore lie in this class and none of the ones below it. So therefore, it must generate all of this class. And it generates this special mod 4 gate, which will generate everything. And then so that's for one gate, and if you have multiple gates, then you do the same process for each gate. And so say you arrive the first time you get a mod 4 gate, and then the second time you say, well, you just lie in this not class. then to see the class for which if the class generated by both gates, by each of the gates together, you take the least common ancestor. So basically, you follow these arrows up to here and follow these arrows up here. This is the least common ancestor of mod 4 and not, and you get to this Fredkin plus not class. So basically, very quickly, it leads to a very quick decision algorithm for deciding whether or not reversible gate classes are the same or not. So very quickly, some techniques used in the proof. That's always nice to have. So suppose we're trying to generate some function, some reversible function f, using the Toffoli gate. So we're trying to show the universality of Toffoli, but we're trying to show it in this model where we're not allowed any input-dependent garbage. So notice so this is the Toffoli gate, but if I replace this t here with a 1 in Scylla, then this last bit here, this is just a NAND gate. And we know that NAND is universal for computation in the sense of many-to-one functions. And we can think of f as just n independent many-to-one functions. And therefore, we can basically create the transformation where we have x, and then using this intuition of having a bunch of NAND gates at our disposal, we can create the transformation x goes to x, some garbage of x, which is like basically all the intermediate steps in our computation, and f of x. So we're sort of close to generating f of x, or this transformation here, but we still have this input-dependent garbage left over, and that's no good. So to recap, we're trying to generate f, and we've generated this string so far. But now we still have a Toffoli gate, so we can use that to generate a C0 gate, as we showed before. And a C0 gate is basically just a copy gate, so we can copy f of x into another register. So now we have 2 copies of f of x. And now this is where we use the property that we're working with reversible gates, and we use this trick called uncomputing, which is basically, since we can take x to x garbage of f of x, well, we know we have the inverse as well, so we can take x garbage of x f of x to x. So now we apply that function in reverse, and we get this. So we're pretty close, but we still have this x lying around, and we want to get rid of that. But basically, we just do the same thing. So now we know we can, since we can compute f, we can do the same thing with f inverse. So we can apply f inverse to f to get f of x garbage of f of x x. We can use our Toffoli gate to copy one of the x's into its own register to get x, and then we uncompute again to get f of x. So that's sort of a mouthful, but maybe it was OK. But you might notice sort of an issue here. And the issue is that we used a bunch of ancillas here. OK, cool. I'm almost done. So we used a bunch of ancillas. And so basically, one of the consequences of our classification is that we actually get rid of all these ancillas and compress them down all just to a constant number. Open questions, the obvious one being, can we finish this? Luke and I have almost basically done the Clifford gates. You can think about 1 and 2 gigabit gates. You can think about Hamiltonians, which is sometimes nice because you get a continuum of gates to start off with. You can think about different ancilla rules. Perhaps most apt for this talk is you can think about different arity. So instead of doing the classification over bits like we did, you can think of trits and so on and so forth, which we know is going to be much more complicated. And that's it. Thanks.
So I understand what this mod 2, mod 4 is, but can you give a simple explanation of what Fredkin plus not generates? That's not everything?
Yeah, that's a good question. So think of any circuit that has composed of Fredkin and knots. So the Fredkin is conservative, and the knot is always going to flip the Hamming weight. So if you think about the entire circuit is either always going to conserve the input, the parity of the input, or it's always going to flip the parity of the input. So any circuit you build is going to have that invariant. It's either going to always conserve the parity of the input or always flip it. But there are obviously some transformations that sometimes flip it and sometimes don't, depending on the input.
But then if it's one that flips, it could be arbitrary it could be any permutation that flips Hamming weights.
Yeah.
What are the general rules for, let's say, like a mod 6 gate? Like
what's
for a mod 6 class?
what's the generator?
Yeah.
The generator is it's a 6-bit gate. If all of the inputs are 1, it flips them all to zeros. If they're all zeros, it flips them all to 1s. Otherwise, it does nothing. This will generate every non-affine gate that preserves Hamming weight mod 6.
So you said that before they did classify reversible circuits without this ancilla rule.
Yeah.
What did that lattice look like, and why is this more insightful?
So that lattice is actually pretty boring. I mean, it's cool, but it's basically like all non-affine gate sets, all affine gate sets, and all degenerate gate sets. They all kind of glorp down to one thing.